All right, section 3.1. Sarah, have you graphed anything on your calculator since I showed you how? Okay, is there anybody else that hasn't used a graphing calculator? Okay, I didn't think to tell you to make sure that you had it today. We're going to graph everything that we're going to do by hand, but then I also want to show you how to do it on the calculator so that you can check your answers. On this test, I would want you to know what these graphs look like, but like I've said about the other graphs we've done so far, you should have a quick mental image of what the graph looks like before you pick up your calculator so that if you type in something goofy or if your Windows set something crazy, at least you know what the graph should look like and you know to go check your settings. The four special cases we're going to look at, y equals x squared, you know it's a concave up parabola with vertex at 0, 0. Y equals negative x squared is a concave down parabola with vertex 0, 0. X cubed is that going uphill snake-like shape. And then negative x cubed is the reflection of that with respect to the x-axis. Now, what I didn't realize in high school, I'm not sure if I was not taught it or if I just wasn't paying attention the day that it was taught, but what I didn't realize is that all polynomial functions have that end behavior, and you can tell by just looking at the first term what the end behavior of the graph is going to look like. The end behavior of the polynomial function f of x equals, that's just some coefficient times x to a power, is determined by two things: whether the sign of that leading coefficient is positive or negative, and whether the degree of the polynomial is even or odd. Turns out all even degree polynomials, and the degree is just the highest exponent, all even degree polynomials with positive coefficients do the same thing on the end as x squared. Both ends go up. All even degree polynomials with a negative coefficient look like negative x squared on the ends. All odd degree polynomials with a positive coefficient look like x cubed on the end, left end going down, right end going up. And all odd degree polynomials with a negative coefficient look like negative x cubed on the end. So for example, if I ask you to graph f of x equals x to the sixth, let me make these easy, label these so it'll be easier for you to answer the questions I'm fixing to ask. I'm going to call those graphs A, B, C, and D. Which one does x to the sixth look like? Yeah, it's even degree with a positive coefficient. So both ends go up, just like x squared. Now what you can't tell without graph paper or making some nice tick marks is that x to the 6 is much steeper than x squared. And that makes sense because when you raise numbers to the 6th power, they get big a whole lot faster than when you just square something. We're just talking about end behavior right now, not width. What about f of x equals negative x to the 5th? A, B, C, or D? Which one does it look like? Yeah, it's odd degree with a negative coefficient. So at least on the ends, it looks like negative x cubed. It's going up on the left and down on the right. It's a decreasing function. Now that takes care of the end behavior of the graph. Everything you know about horizontal and vertical shifting still applies to the graphs of polynomial functions. You know what shifts a graph to the left or to the right, what shifts it up or down. The graph of a times x minus h to the nth plus k. H is your horizontal shift, and it still works the opposite of what you might have expected. K is your vertical shift. Adding k moves the graph up, subtracting k moves the graph down. But that's the same as the graph of a times x to the n. What you would have if you multiplied that all out and put it in general form, you can still determine the end behavior of the graph by looking at that leading term, but the graph is translated horizontally h units and vertically k units. In the last chapter, we would have graphed y equals negative 1 times x minus 1 squared plus 5. What does that graph look like? What type of graph is that? It's a parabola because of the square. It's concave down because of the negative. And then where is the vertex of that parabola? Positive 1, positive 5, because that horizontal shift works the opposite of what you expect, and then the 5 shifts it up 5. So this example, f of x equals negative x minus 2 to the 4th plus 1. What's the end behavior of that graph? Is it the same as A, B, C, or D? Yeah, it is even degree with a negative coefficient. So I know that it goes down on both ends. And I'm going to stop calling this the vertex. I'm just going to call it the turning point, and I'll tell you why in just a minute. What is the turning point or the critical point on that graph? It's been shifted to the right 2 and up 1. I'm going to call it TP for turning point, is positive 2, 1. Now, if I want more particulars, like what are the x-intercepts, the y-intercepts, I'll ask for those. Right now, we're going for end behavior and turning point. What about example B? F of x equals x plus 4 cubed minus 2. The end behavior of that graph looks like C. It looks like x cubed because the degree is odd and the leading coefficient is positive. So it goes down on the left, up on the right, and has been shifted so that its turning point is what? Negative 4, negative 2. Now here's why I'm calling that point negative 4, negative 2 a turning point. I couldn't call that a vertex, but something definitely happens there. The shape of the graph changes right there. Excuse me. In calculus, we're going to call that an inflection point. It's actually where the concavity of the graph changes. Now that's just kind of a preview of what's coming, but that's why I'm calling that a turning point and not calling it a vertex. All right, big number 3. A polynomial of the form f of x equals some leading term plus the other terms arranged in descending order has the same end behavior as determined by this leading term. In other words, and this is what I didn't realize in high school, no matter how big and ugly the polynomial is, you can still tell the end behavior just by looking at the first term. So if you give me y equals negative 3x to the 7th plus 2x to the 6th minus 5x to the 4th, and it just keeps going down to my constant, to determine the end behavior of that graph, I only have to look at the first term. Now what the other terms effect is how many squiggles in the middle. Just because a graph goes down on the left and up on the right doesn't mean it doesn't squiggle around some before it has that end behavior. So my note number 4 has to do with how many squiggles can be in the middle. A polynomial function of degree n has at most n minus 1 turning points. In other words, a 5th degree polynomial cannot squiggle around more than 4 times in the middle. And then you can tell by the 5th degree and the leading coefficient what the end behavior of that graph looks like. The intermediate value theorem makes sense if you think about it. Doesn't even seem like it should have its own special name. If a polynomial with only real if f of x is a polynomial with only real coefficients, and if for the real numbers a and b, the values of f of a and f of b are opposite in sign, then there exists at least one real zero between a and b. One thing that you're going to get good at in this course and in calculus and however far you go on, you're going to get better at reading mathematical theorems and figuring out what the heck they mean. What do you know about f of a and f of b, or just f of x? F of x is equivalent to what? It's some y value. This is some y value when x equals a. This is some y value when x equals b. So I could try to draw a picture of what the intermediate value theorem is telling me. There are two x values, a and b, and f of a and f of b are opposite in sign. F of a might be positive. If f of a is positive, then f of b is negative. Or it could be the other way around. F of a is negative and f of b is positive. But all the intermediate value theorem is telling me is if I have these two real numbers, a and b, such that f of a and f of b are on different sides of the x-axis, then somewhere between a and b, the graph has to cross the x-axis. That's all it's saying. There is a zero. To get from here to here, you have to cross the x-axis. So there's at least one real zero between a and b. Remember, interchangeable with the words real zero? What's real zero the same thing as? When you're talking about the graph of the function, what are its real zeros? The x-intercepts. So if you can find two x values, a and b, such that f of a and f of b are opposite in sign, then somewhere between a and b there has to be an x-intercept. All right, here's where I'm going to start asking for more specifics. And when you do the homework, I want to see on each problem part 1, part 2, part 3, part 4. Or I wish I'd called it A, B, C, and D. Doesn't matter. The first thing I want you to identify is the end behavior of the graph. Does it basically look like x squared, negative x squared, x cubed, or negative x cubed on the ends? Second thing I want you to do is find the y-intercept by letting x be 0. And then find the zeros of the function, the real zeros of the function, which are the x-intercepts of the graph, by letting the whole thing equal 0. And then part D, give the x values for which f of x is less than 0. When you look at that, just think, give the x values for which the y's are less than 0, and then give the x values for which the y's are greater than 0. Now, one other thing before we do these examples, just a note from the college algebra book, and this note is later in the pre-calculus book, but comes in darn handy now. Do you remember the word multiplicity from college algebra? If you have a function, let's say f of x equals 3 times x minus 2 cubed times x plus 3. I'm sorry, what? Did I say x minus 3 and wrote x minus 2? Doesn't matter. I'm just making up a polynomial here. Let's make this x plus 3 squared. What degree is that polynomial? If I multiplied it all out, which would take a little while, but if I did, what would be my highest power of x? Yeah, it's a 5th degree polynomial. And the fact that the leading coefficient is positive tells me that the graph goes down on the left and up on the right, like x cubed, with no more than how many squiggles in the middle? No more than 4 squiggles in the middle. All right, now here's the note from college algebra. The multiplicity of a zero is the number of times the factor that gives you that zero is multiplied by itself. Let me try that again. I didn't say that as well as I could have. The multiplicity of a zero is just the exponent of the factor that gives you that zero. In other words, if you set x minus 2 equal to 0, you would get 2 as one of the x-intercepts of this function. Because x minus 2 is to the 3rd power, you would say 2 is a 0 of multiplicity 3, because that's the exponent of the factor that gave you 2 as one of the x-intercepts. And then you could say negative 3 is a 0 of multiplicity 2, because that's the exponent of that factor. And the reason that we need to know the multiplicity of each zero is whether that multiplicity is even or odd tells us something about the graph at that point. And here's the note from college algebra. If R is a zero of even multiplicity, in other words, in this example, negative 3 is a zero of even multiplicity, the sign of the function does not change from one side to the other of R. Or here's, in my opinion, a better way to say it. The graph of the function touches the x-axis but doesn't cross it. In other words, this graph at negative 3, the graph is either hitting negative 3 and doing a U-turn, concave up right there, or it could be coming from below, hitting negative 3 and doing a U-turn and going back down. Touches means touches but does not cross. It's either all above the x-axis or all below the x-axis. If R is a zero of odd multiplicity, then the graph actually crosses the x-axis at R. So when we say 2 is a zero of multiplicity 3, that's an odd multiplicity. That means that at 2, the graph is either increasing, hits 2, and then keeps going, or the graph could be decreasing down to 2 and keeps going. But either way, the graph crosses the x-axis at that 0. So now let's look at these 4 examples and do these parts A, B, C, and D. The directions in the book aren't worded exactly that way, but that's what I want you to give me. That's how I want you to label the parts. That's how it is on the test. determine the end behavior, find the y-intercepts, find the zeros of the function. I could say, and their multiplicities, because that tells you what the graph looks like at each x-intercept. And then give the x values for which the y's are negative, give the x values for which the y's are positive. All right, number 16. F of x equals negative 1/9 x cubed minus 3. Yes, ma'am. What? That means I haven't changed my handout to this edition yet. This page I have printed is from the 12th edition. I think it's the right page number. A part, determine the end behavior of that function. Now, if you don't need to write down any words, that's fine. I'm writing words for the folks who need them when they look back at this before they start their homework tonight. This is even or odd degree. Odd degree with positive or negative coefficient. Negative coefficient. Does that basically look like graph A, B, C, or D from the notes? Looks like negative x cubed. It's going downhill from left to right. So when I say give me the end behavior, that's all I mean. And the other thing I know about this graph is it has no more than how many squiggles in the middle? No more than 2 turning points. Now, actually, because this doesn't have the x squared and the x to the first term, I happen to know it doesn't have any squiggles in the middle. It doesn't have any turning points. I need to be careful of how I word that. Yeah, that's what I wrote is correct. What I just said is not correct based on what I said was a turning point. This is going to have a turning point. It's not going to have more than one turning point. Basically, this is just x cubed reflected with respect to the x-axis and shifted down 3, because you don't have your x squared and your x to the first term there. You could think of that as being negative 1/9 times x minus 0 cubed minus 3. So it looks just like this graph, except for it's been shifted down 3. The second thing I want you to give me is the y-intercept. How do you always find a y-intercept? Let x be 0. You let x be 0, you get y as negative 3. And then in part C, how do you find an x-intercept? set the whole thing equal to 0 because you're letting y be 0. Negative 1/9 x cubed minus 3 equals 0. And how do you solve that equation? Yeah, go ahead and get the x cubed by itself. Add 3 to both sides, and then multiply both sides by negative 9. If we wanted the real and imaginary zeros, we'd have to set that equal to 0 and factor the difference of 2 cubes. But since we only care about the real zeros, we're just trying to find the x-intercepts, all I have to do is take the cube root of both sides, and we get the only x-intercept is negative 3. All right, I'm going to go ahead and graph this function. It'll be easier for me to do the D part, tell where the function's positive and where it's negative, by looking at the graph. The x-intercept is negative 3, the y-intercept is negative 3. And I already know the end behavior of this function. I have that in part A. It goes up to the left and down to the right. That's good enough. Yeah, that's good enough. Because what you're trying to do, John, is just get a quick mental image so that if you punch it wrong on your calculator and your calculator gives you a graph with both ends going up, you go, wait, that can't be right. What about at this x-intercept? Negative 3 is a 0 of multiplicity what? Wait, something just bugged me. What was it? Oh, I know what's bugging me. It's not written in that form where you can see the multiplicity very well. Kind of wish I hadn't mentioned that. But to write this in the form where I could see the multiplicity, I would have to have x plus 3 in parentheses, because negative 3 is one of the x-intercepts. And the only way to get that would be to factor out a negative 1/9. I don't care about that. The other problems will be written where you can see the multiplicity of the 0. So this one, because it's just the graph of negative x cubed shifted down 3, I know there's no squiggles in the middle. I'm just going to connect my 2 pieces of the graph there. That wasn't a good example to show you multiplicity, because it was just the graph of negative x cubed shifted down 3. And made a little wider because of that coefficient, but that's where I'm not gonna ask for specifics of how wide that is. If it comes up on my calculator going up on the end to the left and down to the right and has the x-intercept and y-intercept both being negative 3, I'm fairly confident my calculator's correct and I typed that in correctly. So what about the D part? The x values for which the y's are greater than 0. You're giving me an interval. From where to where are the y's positive? If you say x equals 0, you mean the y's start being positive right here. That's not where the y's start being positive. Y is negative 3 there. Look at the graph from left to right. Where does the graph stop being positive? Yeah, at -3 at the x-intercept. The graph is positive from -infinity all the way up to -3, and then it stops having positive y values. So if I'm giving the x values for which the y's are positive, that would be -infinity up to -3. Hey, should that -3 have a bracket or a parenthesis on it? It just says y is greater than 0. Is the y greater than 0 at -3? No, it equals 0, so I should have a parenthesis there. And then all the x values for which the y's are negative. What are the x values for which the y is negative? -3 and then forevermore. That graph's going to keep going down. Now, if we didn't have to write down all that stuff just for note-taking purposes, I could have sketched that graph without writing any of that down. I could have had the end behavior in my head. I could have seen the y-intercept was -3 and the x-intercept's -3, and I could have graphed it without writing down anything at all. Let's try number 20. What's the leading term of that polynomial? The negative x cube's the leading term. It doesn't matter in what order the terms are written. Leading term means term of the highest degree. So if you want to turn that around to negative x cubed plus 9x, you can. You don't have to. But one other thing we want to do on the rest of the problems is write that function factored as completely as possible, because in factored form, it's easy to see the x-intercepts. All I can do to factor that is factor out an x or a negative x. I'd probably factor out a negative x. That would leave me x squared minus 9. Hey, that will factor further. Negative x times x plus 3 times x minus 3. So for the A part, is what's the degree of this polynomial? Third degree with negative coefficient. That should tell you what the graph looks like on the ends. Goes up on the left and down on the right, just like the previous problem. And what about the y-intercept? You can just look at that function. The easiest way to find the y-intercept is before you factored it. Before you factored it, if you let x be 0, what do you get for y? So this graph goes through the origin, 0, 0. And how about the x-intercepts? The easiest place to find the x-intercepts would be where you have the graph or the function in factored form. What are the x-intercepts? If you set 0 or x equal to 0, that's one of your x-intercepts. You have 3 x-intercepts, -3, 0, and +3. Since this is in factored form, it's easy to see the multiplicities of those x-intercepts as well. What's the multiplicity of each one of those x-intercepts? Yeah, the exponent of each of those factors is 1. So the multiplicity of each of those zeros is 1, which is odd. So does the graph just touch, or does the graph cross the x-axis at each one of those x-intercepts? It crosses. That's supposed to be is, not plural. That's all we need to get a pretty darn good sketch of this graph. The y-intercept is the origin. The x-intercepts are -3, 0, and +3. The graph goes up to the left of the leftmost intercept and down to the right of the rightmost intercept. I could have also made a note that this graph has no more than how many squiggles in the middle? Yeah, no more than 2 turning points. You don't have to write that down in the homework. Just give me the M behavior, y-intercept, x-intercepts, and then that part D, along with the graph. The fact that I have already determined the graph crosses the x-axis at each intercept tells me what I need to do here. At -3, the graph needs to go below the x-axis. Now, do I have anything that tells me how far to go below the x-axis? I really don't. That's what calculus is for. One of the things calculus is for. Finding the minimum value, well, not just minimum, not absolute minimum, but the local maxima and minima of the function. Calculus would tell me how far to go down before I turned and came back up. But with calculus, I don't know that. I could find f of -1 and f of -2, but still, if let's say f of -1 was here and -2 was there, the graph may go on down below that before it turns and comes back up. So just finding 2 more points wouldn't necessarily tell me how far down below the x-axis the graph goes. But at some point, it turns around, comes back up, hits the next x-intercept, and then crosses the x-axis again. I don't have anything that tells me how high to go before the graph turns around and comes back down to the next intercept. That's what calculus is for. That's a pretty darn good sketch of that graph, other than not knowing how low to go here and how high to go there. What about the D part, where the function values are greater than 0? Give me the x values for which that function is above the x-axis. Good. Anywhere else? Uh-huh. Yeah. Yeah. Anywhere the graph's above the x-axis. And where does that function have negative values? From where x is -3 to 0, and then where? Yep. Now, let me go ahead and show you how to graph that on a graphing calculator. By the way, if you don't have one yet, and well, if you're an engineering major, you need to go ahead and buy one. If you just have to get through Cal 1 or even just this class, you may just want to get one from the library. The Rome State Library in Harriman will send one to this campus for you. Just go to the library homepage and click Request Delivery, and then choose the calculator you want, and they'll send it by courier right to you in about 2 days. To type in the equation of a function, you pull up the y equals menu. I have something in there probably from last fall. Just clear that. And then the function I want to graph is 9x minus x cubed. I could either type it in as it was given to me, or I could type it in factored form. Should get the same graph either way. Negative x. X is the button right next to the green alpha button. And for exponents, you use the caret key. So negative x plus, or x cubed plus 9x. And then graph is the top rightmost button. And let's see. I must have gotten that error because of some crazy something I had the window set to. To set the window back to standard on the calculator, default is -10 to 10 on the x-axis, -10 to 10 on the y-axis. To set the calculator back to that default, you can just press zoom, which is the middle of the top row, and then number 6 is Z standard. That sets it back to default. Zoom standard, and then what? Is it? Well, that's a good example. Why else would that be? Maybe because I have plot highlighted from statistics. Yep, that's it. Plot 1, plot 2, and plot 3 are not supposed to be highlighted, and I had it highlighted for something I was doing in statistics. Now it should graph. And that's pretty much exactly how our graph looks. But if the previous person who used this calculator had my x's set from 0 to -10 instead of 10 or -10 to 10, then I might not realize that that graph had another turning point in the third quadrant. So that's why I need to have a quick mental image of the graph before I punch it on the calculator. All right, if you've never graphed on a graphing calculator, come see me. The easiest way for me to show you how to do it would be just to bring your calculator to my office or hang around one day right after class, and I can show you what you need to know very, very quickly. All right, We have time for at least one more example. Which do I like best, 22 or 26? 22. We'll do 22, but let me ask you something about 26. Because you need to factor these in order to find the x-intercepts, just tell me how you would factor, where's 26? Yeah, how would you factor 26? Yeah, if it has 4 terms, factor by grouping. Group the first 2, group the last 2, take the GCF out of each group, and then you'll have it. Tomorrow, we're going to talk about how to find x-intercepts for functions that you can't factor in any traditional method. But all the ones in tonight's homework will either be already factored for you, or you'll be able to factor them using methods you already know. So 22, last one. We're going to write down as little as possible on this one because we're about out of time, and because we can get by with writing very little down. The end behavior of the graph, I can tell just by looking at it. On the ends, it's going to look like what? Look like x squared. Going to go up on both ends because of the even degree positive coefficient, with no more than how many squiggles in the middle? One less than the degree of the polynomial, no more than 3 turning points. What's the y-intercept of that function? Yeah, if you let x be 0, you're going to get y 0. To find the x-intercepts, I either have to factor that at the beginning or factor it now. Since I forgot to at the beginning, I'll go ahead and factor it now. I could factor out an x squared, and that would leave me x squared plus 3 minus 4, or 3x minus 4. And that will factor further into x plus 4 times x minus 1 times the x squared. So what are the x-intercepts? Yep. And the 0 is a 0 of multiplicity what? 2, because that's the exponent of the factor that gave me 0 as an x-intercept. And negative 4 and 1 are zeros of multiplicity what? Because that's the exponent of those factors. So this function has y-intercept 0, 0, x-intercepts negative 4, 0, and 1. And I know what the graph does on both ends. Up to the left of the leftmost intercept, up to the right of the rightmost intercept. at -4, does the graph touch or cross the x-axis? Crosses. Do I know how far to go down? Not without some calculus. Turns and comes back up to 0. What does the graph do at 0? It touches, which means it does a U-turn, doesn't cross right there. And then at 1, it crosses again. Let's see how well we did. X to the 4th plus 3x cubed minus 4x squared. Ooh. If I didn't already know something about this graph, I would wonder what's happening there in the third quadrant. Apparently it goes way down there, but only just a tiny bit below the x-axis from 0 to 1. All right. We didn't get to do one of the examples, but that's okay. There was one application I was going to show you, but I think it has to do with, the one in the homework has to do with temperature. You're given a function for temperature, and it says show that the temperature has to be exactly 0 somewhere between 5 a.m. and 7 a.m. You just need to show that the temperature is positive at one of those times and negative at another of those times. Then by the intermediate value theorem, it has to be 0 somewhere in between. It's not really a word problem you have to set up an equation for. You're given the equation.